All right, we're going to look at the second part. We're going to look at thermal expansion in this case. So what is thermal expansion and why is it important? Let's think about this scenario. How do you open a glass jar if the metal lid is too tight? How many of you, now, every year I ask this question, and usually there's one brave soul in the class, especially if it's a class full of males, that will admit to not being able to open a jar. Now, not being able to open a jar is usually my problem. Thankfully, my better half has a little extra strength. But if he's not home, how do you open the glass jar? How many of you have taken a glass jar and run it under hot water to make it easier to open? Running it under hot water causes the lid to expand ever so slightly and usually makes it a little easier to turn off. That's an example of using thermal expansion in an everyday scenario. And now you know the secret to pretend you can open anything. Just heat it up hot enough. I'm pretty sure a lot of you that have worked in shop, you've gotten this far through the year. I'm going to guess you may have seen an example of this already, or you may have seen an example somewhere else. I know this is a common thing that happens if my husband happens to be working on the car. He's got something, or it's not usually the car, it's usually his tractor that he's rebuilt a million times. And he'll have a bolt that's stuck. And when nothing works, the torque wrench won't loosen it. He'll pull out his torch and apply a little bit of heat to see, will heating it be enough to loosen the bolt? So he's using the principle of thermal expansion. Now I'm with you if you say you're never going to have to calculate it, but for the sake of me being the math teacher, I'm going to require you to do a few calculations for this section, but a lot of it you can just think about and do a little bit of logical reasoning to figure out what would happen if. And we'll see by how much is that expansion going to happen. And sometimes it explains things like expansion gaps and whatnot. Now, the formula for linear expansion looks complicated, but it's really, really easy. You're only going to multiply or you're going to divide. So it's a really easy formula to work with. The formula for linear expansion in one dimension is equal to, so if you want to find out what the change of length is when you heat something up, so let's say it's a steel rod and I want to know the change in length. The change of length is going to be equal to alpha, and alpha is a linear coefficient. We're going to get that information from a table. Okay, we're going to get that information from a table. Times the length of the material, this is the original length, times the change in temperature of the material. So that's going to give us our thermal expansion. We'll have a couple examples of this. So I've posted a formula sheet for you. On that formula sheet, at the bottom of it, you should see a section of the chart that looks like this. So this is our table of linear expansion. You'll notice that we have scientific notation for all of these, and that's because they're very, very small quantities. So when I gave you a little bit of a sneak preview, making sure you knew how to put scientific notation in your calculator, it's going to be important here. And if you have forgotten that, I have posted a quick help. I forgot how to use my calculator video to give you a reminder for how to put in scientific notation properly. So please take a look at that video if you're not sure about calculations. Now I'll do a couple of conversions for these just because we'll look at them. So we're going to look, let's look at copper. We're going to take copper because it's a material that all of you use so much. If you're doing electrical work, if you're dealing with copper wires, you've got coils and windings that have a lot of copper in them. If you happen to be dealing in HVAC, all of our hot water rads, there's a lot of copper in those as well. So we'll use copper as our example. So alpha is just a measure of how much it increases per degree Celsius. So 1.7 times 10 to the negative 5 is a very small number. When I see -5, I know I have a small number. That is equal to, let me get the right number of zeros here. So 1, 2, 3, now 0.00017 per degree Celsius, okay? So if we think about place values, I don't even know how, like, I shouldn't say I don't know how to read it. We could figure out what the place value of that is, but it's even smaller than 1,000th. It's 1,000th of, we're talking like thousands of thousands is how much the change is going to be. So it's going to be very, very small, but if you have that change happening over several meters, it can be enough to cause significant buckling. And that's not something we want to have happen. And I'll give you an example of, it's not a structural issue, but where it results in a cosmetic issue that could be avoided if we just thought about how much thermal expansion actually changes things. So these values are all very, very, very small quantities. So knowing how to put them in your calculator in scientific notation will help you. Please check that video out if you're not sure. What I will say right now is, oops, let me go back. What I will say right now, if you're looking for how do I put it in your calculator, look for the EXP button. That EXP button is equal to times 10, the times 10 part, okay? So if you're putting, it could also be EE. So if you're putting these numbers in your calculator, I might put in 1.7, and for my calculator, I'm gonna press EXP, and then I'm gonna put -5, and that will give me the equivalent of that number. So that's just a little calculator tip. All right, so you can check the video out. The video has a couple calculators with some pictures of where the keys are. All right, let's do a calculation question. I love this example. This is not my house. My house doesn't look that bad. But my house that we actually sold it last year, we had to have a heat pump installed. And the only way to connect the heat pump to the electrical panel, because they're on opposite sides of the house, and then there's a slab between the two, so you can't just run things through a basement because there's no basement there. They ran the electrical partially through the basement and then out through the wall, and then we have this lovely gray conduit around the side of the house. Now, when they installed the heat pumps, it was the dead of winter. So we're talking, I think it was about the middle of December. I remember it being very cold and them complaining about the temperature. We were just coming on to a snowstorm. So the temperatures were low. The conduit was beautiful and straight. What do you think happened in the summer? Well, you're going to find that brick retains quite a bit of heat. It absorbs a lot of heat. Because it absorbs heat, it can transfer that heat to other things. So in the summertime, when it gets hot, our conduit heats up. We've got thermal expansion that occurs. And by failing to leave space for that thermal expansion, that flexibility to occur, plastic unfortunately doesn't always shrink back to what it should have been, and you get this lovely warbled conduit around the outside of the house that just doesn't look pretty. So it's purely an aesthetics thing, but that was something that we had happen at our property that maybe it's just me being nitpicky, but every time I looked at it, I would think, now there's thermal expansion in progress, but it's not the kind of thing you actually have somebody fix for you, because it's not something that's actually going to cause an issue. But it is something that from a cosmetic perspective, thinking about what thermal expansion does. So if you're running wires for something, thinking about if I'm installing something in the winter time, is there enough room there for expansion to occur? If you're ever installing flooring, so we've recently put flooring down in our sunroom, and they asked you to give a 1/4 inch gap around all the outside walls. And that 1/4 inch gap is to allow for some expansion and contraction. Now that's more from moisture in wood, but it's the same kind of principle. So just leaving a little bit of flexibility, a little bit of play for thermal expansion to occur can be a good thing. Now let's do the calculations. We're going to figure out how to do a little bit of math. I guess I've talked through most of this. Small changes in length can have serious consequences. Expansion joints are often needed to compensate for changes in material due to temperature. Oh, this is a great one. We've got a road here, and this is an expansion joint in a road. Now, if you think about going across the bridge, now I'm not very good with sound effects, so bear with me, but you're driving across the bridge and you get that da-dunk, 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 you know, that noise that you hear every so often. Those are expansion joints. They need to have those in the bridge, not only to help control sway, because we don't want, if that bridge ever decided to start swaying, and it does sway ever so slightly, it could be catastrophic if they didn't have some of those expansion joints built in, but it also compensates for changes in temperature, because I'm sure most of you have put bare feet on hot asphalt and noticed how hot that can get in the summertime. So that's an added stress on the structure. So they include an expansion joint in order to be able to take up some of that length. There's another example of expansion joints on a bridge. You can see the expansion joint here. And that's not only, it's not just an expansion joint, but it's also to help prevent things like sway. That's a whole nother topic in itself, thinking about how simple harmonic motion affects things. It's not something we have time for in your course. Another place where we have thermal expansion. Why do fluids in the car usually have a reservoir tank? You think about your radiator, your brake fluid, power steering fluid, your oil. As fluids increase, the volume increases, and we need to have some place for that extra volume to go. Here's a boiler. We've got an expansion tank on it as well. We add those in for safety features so that the temperature can go up if it needs to. And there's a place for that fluid. Usually there's plenty of extra room for that fluid. But that's also why if you're filling up a fluid, oftentimes you don't want to fill it up completely to the top. You fill it to the mark, but not overfill, because overfilling can cause issues as well. And that's just because of thermal expansion. One of the places that I really notice thermal expansion is if you fill the gas can for, say, your lawnmower or something like that, and you're mowing on a sunny day, it may have been sitting in the shade when you filled up, and by the time you get back to it, the sun's been on it, and you'll notice it puffs right out. And there's another example of thermal expansion, but that's thermal expansion in a volumetric sense. And we'll see some example calculations of that too. Another place where we use thermal expansion, I've got lots of examples in here for you, just because I really like thinking about these examples. I find them interesting to see where they happen in your home. But because mercury is toxic, mercury, the story of the Mad Hatter from Alice in Wonderland, if you're familiar with that, the reason they called them the Mad Hatter was when they made hats. They made hats from mercury. The mercury would leach into the person's head, and it affected their cognitive abilities, which made people say that they were mad. So because we know that, we no longer process hats with mercury anymore. So it was during the days of beaver felts and furs, that was commonly used there. But now what we do, now that we know that, we're trying to phase mercury out of household products just for the sake of the environment and safety of individuals in the house. So a lot of our thermostats no longer have mercury in them. We did have a mercury thermostat in one of our houses. That was something I noticed. It's just the difference in aging and how things have changed. But a lot of our thermostats now have a bimetallic strip. So it's made from 2 strips of metal that have different coefficients of linear expansion. So one side expands more than the other. So in this case, brass expands more than steel. Because it expands more than steel, it's going to cause the switch to bend. Depending on how much the temperature change is going to cause a larger bend. If there's more temperature change, a smaller bend. if there's less. So because that strip bends with temperature change, we can use that to activate a thermostat. When it's likewise, when it's cooled, as it cooled, a temperature change in the other direction is going to cause it to bend back the other way. So we can have temperature occurring in both directions, just because steel has a smaller coefficient of expansion. So that's another good example of thermal expansion, and something you can take a look at. Hey, if you pop the cover off your thermostat at home and see, is your thermostat mercury based, or does it have the bimetallic strip? All right. Let's do some calculations. Finally, I said the calculations were about 4 slides back. Once we've done the calculations, we're done for this section, so you've got all my ramble. So our question here, we have a steel bridge, it's 2 kilometers long. If the temperature when it was built was 21 degrees Celsius, what is the length of expansion joint needed to prevent buckling at 43 degrees Celsius? So this is a question that's got all your information. We don't have to actually do any rearranging because we've got 2 temperatures. So we have 2 temperatures, and we happen to know the length of our bridge. And we want to know what length is the expansion joint, or what's the change in length going to be given these parameters. Now alpha, so I've got the original length. I can figure out the change in temperature. Alpha, this is our coefficient. And it's on the chart. Okay? So the coefficient is on the chart. So I'm going to pop the chart up here. So our bridge was made of, let's go back here. Our bridge was made of steel. So if I go to the chart, steel, if we find steel, this is a linear expansion. It's the length that's changing. So the coefficient for steel is 1.3 times 10 to the negative 5, okay? So we're going to go back to our question. So alpha for steel equals 1.3 times 10 to the negative 5 per degree Celsius. Now that alpha is in degrees Celsius, so that means my temperature needs to go in degrees Celsius when I put it into the equation. So let's figure out what we need. So we need to find what's the change in temperature. The change in temperature, well, it started out at 43 degrees, and the temperature dropped to 21 degrees. So 43 minus 21 gives us a 22 degree Celsius temperature change. Now we can put that into our equation to find the change in length. So change in length is equal to, we take our alpha, which is 1.3 times 10 to the negative 5 per degree Celsius, multiplied by the original length. The original length was 2 kilometers. Now let's think for a second. If I want to find out the length of the expansion joints, does it make sense that an expansion joint is going to be kilometers long? Not really. What I usually suggest in a question like this is think about how big your expansion joints or expansion amount is going to be. It would probably make more sense for me to measure the expansion amount in centimeters or meters. So what I'm going to suggest is, before we even do our calculation, let's switch kilometers into meters. And we have 2,000 meters. That just means when we get our change in length, it's going to be in meters, which is a more appropriate quantity for determining the expansion joint. So 2,000 meters, and we can use whatever unit for length we happen to want. Whatever unit we put in for length, we'll get the same unit out for length because the unit won't cancel. Times their change in temperature, which is 22 degrees Celsius. So we'll take all of that and we'll put that into our calculator. So 1.3 times 10 to the negative 5, I'm going to put Celsius on the end of this, times 2,000 times 22. leaves us with a change in length of 0.572 meters. So Celsius and Celsius cancel. We get our unit length for units. Our unit for length comes out as meters. So the change in length is 0.572 meters. So about half a meter. If we go with sig figs here, we wouldn't want any more than 2. We could say 0.6 meters or 0.57 meters. I didn't specify rounding, and perhaps I should have had the 2 kilometers a little bit more precise for you. Okay, so those are just, if you were calculating and you rounded a little bit differently, 0.6 or 0.57 will give us all the same values. So about half a meter of expansion joints. 2 kilometers is a decently long distance. That sounds about reasonable. If you divided it between, say, 10 expansion joints, each of them only ends up being 5 centimeters. That's not enough to impact a tire. And if you think about how much space is between each of these fingers, that sounds like a reasonable quantity. All right, got an extra slide in there for you. Let's look at the other calculations for thermal expansion. We're going to look at the thermal expansion for area and for volume. So there's 3 formulas altogether. Deciding which formula to use, ask yourself, is it a length that I want, an area that I want, or a volume that I want? Okay, asking those 3 questions will help you figure out which formula. So the last question was the bridge. We want to know the change in length. So we're going to use the expansion formula for length. If we want to find out a change in area, you're going to use the expansion formula for area. If, on the other hand, we want to find out what's the change in volume, we would use the volume thermal expansion formula. It looks almost the same, except alpha gets changed to beta. So there's another constant, and that again is on our chart. So it's there for you to use, and rearranging is no more complicated. With area, the formula is almost the same, but you double alpha, okay? Or you double your coefficient. So I'm going to do a question with volume. I won't give you a question with area, but I will post a worksheet of sample problems that I'd recommend you do 2 or 3 of. The answers are at the end of each of the questions for you to check as you go so that you know if you're on the right track. A 64-liter heating system is completely filled with water at 18 degrees Celsius. How much water overflows if the system heats up to 95 degrees Celsius while in operation? So this question, we have 64 liters. This tells me I'm doing a volume question. So I'm going to want to find a change in volume. The formula for that is beta times volume times the change in temperature. Now let's just make a little table of values that we can use to figure out our question. So beta, that's our chart number. We'll look it up. Volume is the original volume, so we had 64 liters. And then the change in temperature is equal to 95 minus 18, which gives us 77 degrees Celsius. All right, so we have most of our information. We just need the number from the chart. So the number from the chart, we are looking at, let's see, it was filled with water. So volume, so volumetric expansion, that's our beta there. Now for water, it's 2.1 times 10 to the negative 4. So let's go back and put that into our question. So 2.1 times 10 to the negative 4 per degree Celsius. So let's plug it in. We want to find the change in volume, and a little triangle just means change, is equal to beta is 2.1 times 10 to the negative 4 times 64 liters times 77 degrees Celsius. So putting all of that number into the calculator, Give me a second. Let you plug it in as well. It would be a good move to follow along. We get a change in volume equal to 1.0 liters. So you'd have 1 liter of overflow. So that's why we've got that expansion tank on that boiler, is to allow room for that 1 liter of water to overflow. I'm sure there's other reasons for having the expansion tank. For those of you that are in HVAC, I'll let you fill me in on all the details for that, perhaps when we see each other again. Sounds like it might not be until next year. I've got everything twice, and that takes us to the end of the second lesson. Take a few minutes, please, and do the questions, the worksheet that goes with this. Try to do at least 3 questions from the worksheet. It'll just really help you out for doing the quiz. Once you finish the worksheet questions, there is a quiz. Quiz number 1 for thermodynamics covers the first 2 lessons that you've watched so far.